Okay, geometry, we're going to get going into section 4.5 right here. And depending on what year this is and what I'm planning on doing, we might be doing this a little bit out of order. And if that's the case, that's because if we're not that worried about the formality of two-column proofs here, everybody, a lot of the material we're going to cover in 4.5 is easier than what was going to be covered earlier on in the chapter. And the big thing that I wanted to talk about with you guys earlier on now in this chapter is this concept we're going to get into right now of classifying triangles. You'll notice from the title that we're going to be talking about isosceles and equilateral triangles, but we better figure out what those things are before we actually try to learn anything about them. So, classification of triangles is something you guys may very well have done in some previous math classes, maybe in elementary or in middle school, but I think it's worth talking about right now. To give you the scope of what's happening here, guys, I kind of have a table here with 2 columns and with 3 rows here. And there's no reason that this has to be organized this way, but I think this is useful to realize that there's 2 big ways of classifying triangles. One of them is by side lengths, so that's what's going to happen in this first column, and the second way is by angle measures, and we'll talk about all of that in the second column here. So when we talk about classifying a triangle by its side lengths, everybody, 3 different types of triangles we can come up with. And the first one here, I don't know that it matters too much what order we do this in. I'm going to go ahead and talk about, let's go with the most descriptive and specific one first, and that is going to be an equilateral triangle. Now, if you're going to get really good at geometry, everybody, or really good at math in general, you kind of have to have a little bit of an understanding of language, all right? And if we break down the word equilateral, this is something you'll hear me doing a lot of further on in the year. Let's see, it's basically in 2 chunks right here. The EQUI at the beginning sounds a lot like the word equal, all right? The lateral at the end here means side. You'll talk about the latissimus dorsi muscles being the ones on your side and your back and the flank a little bit. In football, a lateral pass goes off to the side. In something in politics, if it was a bilateral agreement, bilateral means two-sided, like Republicans and Democrats worked together on something. So equa means equal, lateral means sides, and if you can understand those words here, guys, we can understand that an equilateral triangle means a triangle with 3 congruent sides. So that's what we're right here. An equilateral triangle has 3 congruent sides to it. So our picture of an equilateral triangle is going to be pretty easy to draw. In fact, I'm going to go ahead and cheat here, guys. Let's see, my smartboard has a tool for this, I believe, and my equilateral triangle might look something like this. Now, one of the most important things we've talked about all year is that we should not make assumptions from a diagram. So if I want to indicate that this triangle is equilateral, I need tick marks, the same number of tick marks on all 3 sides. And that once you've drawn that, everybody, now we can see from the red tick marks that all 3 sides of that triangle are congruent, and that makes it equilateral. So equilateral, equal sides. That's what that one means. The next one, everybody, is called an isosceles triangle, and this is a really commonly misspelled word here. Isosceles is I-S-O-S. I have to say that to myself because I forget it a lot. C-E-L-E-S. And an isosceles triangle, everybody, this one I think uses some Greek roots that I don't know real well, so I don't think this one breaks down in any way to tell you what's going on. And the definition of an isosceles triangle is a little bit tricky. Technically, an isosceles triangle has at least 2 congruent sides. Now that at least right there, I'm going to put in parentheses. In most cases, everybody, you're okay ignoring that at least. And you can just think of an isosceles triangle having 2 congruent sides. But more formal geometry books out there like to keep the at least in there, and the reason for that is because every property that we're going to learn here that applies to isosceles triangles also applies to triangles that have more than 2 congruent sides. Well, if we're talking more than 2 congruent sides, that must mean that we're talking about 3, and that means that technically, you guys, an equilateral triangle is also isosceles. Now that gets confusing and I'm not really sure that's important. So like I said, you can kind of ignore the at least right there and just think that an isosceles triangle has two congruent sides to it. Now, when people think about an isosceles triangle, I think I've got a tool for this one too here, guys. They tend to think of an isosceles triangle either being tall and skinny, you know, maybe something like a Christmas tree, or you can make it really short and wide. And that shape right there, you see a lot in architecture, everybody. If you were to study the Parthenon in Greece, you see a lot of Greek structures that have columns that look something like this. Okay. It's also entirely possible, maybe without that level of formality, your house uses that shape in it as well. If I were to look at my house from the side, I live in a two-story, everybody, but my roof is, ooh, that was ugly. My roof is more or less symmetric when viewed from the side. And so if you were to think about this shape right here, a lot of our houses have isosceles triangles that make up the pitch of that roof. All right, so you're going to see that shape all over. It's one that shows up in architecture a lot. I'm going to go ahead and leave this one right here as our example of an isosceles triangle, but I drew that, oh, that was ugly. I drew that big, you guys, on purpose, because within an isosceles triangle, there's a lot of vocabulary that we need to know. Now, for starters, I better show that we've got congruent sides. So I'm going to say that this side on the left is going to be congruent to this side on the right, but that those two sides are not congruent to the bottom. Let's get our vocab down, guys. In an isosceles triangle, the two congruent sides are both called the legs of your isosceles triangle. We need to know that. And the third side, okay, now this is a little bit misleading. The third side is called the base. And what's dangerous about that is when we all hear the word base, we instinctively think of location and we think base must be on the bottom, because we hear the word basement or the base of a statue and we think, oh yeah, base means on the bottom. That is very often the case, but it absolutely doesn't have to be the case. Don't write this down, guys, but if I were to draw a triangle that looked something like this and say that side is congruent to that side, let me go back to the definitions I said just a second ago. The two congruent pieces are your legs. So that's a leg and that's a leg. And the definition of a base is not the bottom side. The definition of a base is the one side that's not congruent to the other two. So in this case here, the base is located over on the left. And you could just as easily flip these diagrams around to put the base on the top or the base on the right, or just kind of hovering out wherever. So we want to make sure that we understand that base does not mean the bottom side. That's actually going to be an incredibly important and challenging thing for us to master later on in the year when we get into surface area and volume of three-dimensional solids, which we're probably going to be covering in May, if I had to guess, everybody. Base does not necessarily mean bottom. Okay, so in an isosceles triangle, those are the names of the three sides. Going a little bit further, you guys, the three angles in an isosceles triangle, they have names as well. Now, these two angles down here, this guy and then this guy, those are the two angles that touch the base. So, as it might make sense, those are going to be called your base angles. Okay? The way I have it drawn now, there's one on the bottom right and one on the bottom left, but they don't always need to be there. And as I think you can tell here, guys, that wasn't really an accident on my part. I put one tick mark in each one of those angles, which should tell you something that you may have assumed anyway, but we'll get to that in just a moment. The third angle, everybody, the one that doesn't touch the base, the angle that's between the two legs, which in this case is up here on the top, that angle right there, ooh, I'm running out of room, that is called, everyone, your vertex angle, which is kind of a stupid name because every angle that we draw has a vertex. But anyway, within the context of an isosceles triangle, the vertex angle is the one between the legs, the one that does not touch the base. Okay. So where are we now, guys? We have an equilateral triangle, which has three congruent sides, an isosceles triangle, which really has two congruent sides, and so the third one must have one congruent side. But if you think about that, that doesn't make any sense. A triangle can't have just one congruent side because it's not congruent to anything else. And the word here, I think, is another Greek root right here that we don't know real well, and that's going to be a scalene triangle. And a scalene triangle is one that is going to have no congruent sides. Or simply put another way, guys, three sides that are all different lengths. So to draw a scalene triangle, I usually like to draw it with an obtuse angle, looking something like that, and I try to make it clear that one of those sides is longer than the other. And if you did it with a right or an obtuse angle like I just did, when you now draw the third side, that one is going to be longer than either of the other two. Now, what I'm about to do with tick marks doesn't prove the point that I wish that it did, but if I put different tick marks on all three sides here, that seems to suggest that all three sides are different lengths. That's actually not 100% accurate. When we see tick marks in a diagram like this, it doesn't guarantee that these three sides are not congruent. It simply says that we don't know for a fact that they are. And there's not much to say about a scalene triangle, you guys. It's just kind of there, and there's no vocab because there's not really anything special about it. So those are the three types of triangles that you can make by their side lengths. 3 congruent sides is equilateral, 2 congruent sides is isosceles, and a scalene triangle means that it has no congruent sides. So let's go ahead and shift now, transition over to the right side of this table, and talk about how to classify triangles by their angle measures. And these three classifications, I think you guys are going to recognize the names of. The first one here, everybody, is an acute triangle. Now, yes, we know the word acute already. We've learned it all year long, but what we've been talking about is an acute angle. Now we're talking about an acute triangle, but as you could probably guess, they're related to one another. An acute angle is one whose measure is less than 90 degrees but more than 0. An acute triangle is a triangle then that has 3 acute angles. Okay, so all 3 of the angles in an acute triangle have to be acute. So I'm going to freehand a drawing right here, guys, and say, this is always harder to draw than I think that it probably should be. But if I were to draw something that looked like this, okay, yeah, let's run with that. All right, and let's just go ahead and give one example of a triangle that has 3 different acute angles. But I do need to remind everybody of this pesky rule that we can't quite get around, ladies and gentlemen, which is that in any triangle, the sum of your 3 angles must always be 180 degrees. Now it looks like this angle right here, I almost goofed up and almost drew it as a right angle. I'm going to say that that one is 80 degrees. Yeah, and we're going to run with that. Now let me think about this, guys. That leaves 100 degrees left over for my other 2 angles to share. So what if I said now that this one, which looks a little bit sharper than the other one, was about 60? 80 and 60 is 140, and that would leave 40 degrees left over for my third angle there. Okay, that's an example, everybody, of an acute triangle for the very simple reason that it has 3 acute angles. Not that bad. All right, the second one we're going to talk about after an acute triangle is going to be a right triangle. Now, an acute triangle, we just said, is one that has 3 acute angles. Therefore, it would kind of be logical if you looked at this and said, if an acute triangle has 3 acute angles, a right triangle must have 3 right angles. But if you start doing the math on that, 90 plus 90 plus 90, that gets you 270, which is a little bit more than that 180 right there. So that's not going to work. A right triangle is a triangle with 1 right angle. And then by extension, let's think about that. If our one angle is 90 degrees and the sum still has to be 180, that leaves 90 degrees left over for the other 2 angles to share. Now, neither of those angles can be 0. They both have to have a positive angle measure. So if 2 angles together have to add up to be 90 degrees, then each one of them on their own must be less than 90, which means acute. So a right triangle has 1 right angle and it has 2 acute angles. So that's what we need to know about a right triangle, okay? And the diagram we're going to draw for this one right here, everybody, let's see, I think I can cheat and use a tool for that one too. Okay, so a right triangle, and that was ugly, okay. Not sure what happened there. All right, so a right triangle, we're going to cheat, we'll just do it this way. But we need to leave some room here, guys, because there's vocab within a right triangle as well. To indicate, everybody, that one of your angles is right, well, like always this whole year, we're going to go ahead and make a little corner mark right there. That's our 90-degree angle. And as far as the vocab is concerned, you guys might know these words from studying the Pythagorean theorem in some middle school courses. The side that is opposite or across from the right angle in your right triangle has a big funny name here, everybody. That is the hypotenuse. We're not going to use that word a ton in this chapter, but we're definitely going to use it a lot later on in the year. So again, the side that's across from the right angle, that's the definition there of hypotenuse. The other two sides, the ones that actually meet right here to form the right angle, those are called the legs of a right triangle. And if you notice, everybody, here's the word leg popping up as a vocabulary word again when we just used it over here on the left when we were talking about isosceles triangles. So that can get a little bit confusing, but we've got to take the time to make sure that we get all of that understood. So that's a right triangle, everybody, and that's all the vocab that we need here. And the last type then, well, you can probably figure this out. If we've talked about an acute triangle and a right triangle, well, sure enough, there is an obtuse triangle. Now, an obtuse triangle is clearly going to have an obtuse angle, but it can't have more than one for the same reason we saw with a right triangle here. So an obtuse triangle is one that's going to have one obtuse angle, and sure enough, just like in a right triangle, the other two angles are going to have to be acute in order for those three angles to all add up to 180 degrees. So actually, guys, I'm just going to be really lazy right here, and I was going to steal my diagram right there that I drew for a scalene triangle and move it. Oh, really? Well, never mind. All right, undo that, undo that. Let's just do this the hard way. All right, so again, I try to draw a clearly obtuse angle now, and then connect them there, and there we go. Now, there's no great way of showing this as an obtuse triangle, but if I were to guess, that large angle has to be more than 90, so I'm going to guess that that's 110 degrees. The other two angles then, let's think about that. 180 minus that 110 is going to leave us 70 degrees left over. It doesn't look to me like this angle and this angle are congruent. So if I thought about that, 180 minus 110 leaves us 70 degrees. An even split of those two angles would be 35 degrees. But I don't think that's an even split. I think that this angle right here looks smaller than this angle here. So I'm going to guess that the sharper angle, the one in the bottom right-hand corner, is going to need to be less than 35 degrees. So I'm just guessing here, guys, but maybe this one is like 25 degrees, 10 degrees less than that. Then the other angle would have to be 10 degrees more than that in order for them to average out at 35. And this is one example of what an obtuse triangle might look like. Now, guys, everything right there, those are the important ones that are worth talking about. I do want to introduce one other little idea here, though, and I hate to tack more on at the end right here, but this is almost like a fourth way of classifying a triangle right here. You'll see this one from time to time. Equiangular. And way back at the start of this, everybody, we defined equilateral to mean three equal or congruent sides. An equiangular triangle, I'm hoping you guys can tell me, means equal angles. So our definition of an equiangular triangle is going to be three congruent angles. Now, if you think about that, you already know that the sum of the three angles in any triangle has to be 180. And so, if they all need to be congruent, you could just take 180 and divide it evenly by 3, and you're going to find out that all of your angles in an equiangular triangle, if all three of these are congruent, they all have to have this same measurement of 60 degrees. No ifs, ands, or buts about that one, guys. In an equiangular triangle, all three of your angles have to have a measure of 60 degrees. Okay, and that kind of puts a bow on all of the classifications of triangles, and now we're going to learn a few things moving forward that tell us what it is that we can do with that information. Okay, and let's move on from here, guys. So, after that, we're going to get into a couple of theorems here in this section, neither of which is really all that bad. So theorem 4.3, its title is the isosceles triangle theorem. You guys don't need to know the names of these at all, but what it says is important, guys. If two sides of a triangle are congruent, then the angles opposite those sides are congruent. Remember that most of our theorems in what we call are written in what we call if-then form. So the if is the hypothesis, and that's what we read in order to draw ourselves a diagram. If two sides of a triangle are congruent. So what I'm going to do here, guys, is draw a triangle that has two sides that are congruent. Now, back to the definitions we just got done writing down, that's what we mean when we talk about an isosceles triangle. So to try to make this look good, everybody, I'm going to go ahead, I think I was there already, wasn't I? I was going to go ahead and use my isosceles triangle tool and draw one that maybe looks something like, yeah, we'll run with that, kind of a Christmas tree shape right here. If two sides of a triangle are congruent. So this particular triangle, I'm going to go ahead and label this triangle A and B and C. So you can call it triangle ABC or triangle CBA or triangle BAC. There's 6 different ways of naming it. And we now want to say, because of the hypothesis of this theorem, that 2 of those sides are congruent. The way it looks like, guys, it looks like we've got line segment AC that looks like it's going to be congruent to line segment AB. So this diagram right now completely summarizes the hypothesis of this theorem. If two sides of a triangle are congruent. And now, the conclusion now comes from the then. Then the angles opposite those sides are going to be congruent. So the 2 sides that were congruent were segment AC and segment AB. Let's kind of paraphrase what's going on right here. If segment AC is congruent to segment AB. That's kind of what we can see here. Then the conclusion now is that the angles opposite from those sides have to be congruent as well. So line segment AC is this side over here on the left, and the angle opposite from line segment AC is angle B. AB, line segment AB, is the line segment over here on the right, and the angle across from or opposite that would be angle C. So this theorem seems to be telling us now that angle B would have to be congruent to angle C. And that's really the takeaway from this. Now, what I want to draw within the figure are the tick marks here that show you that angle B and angle C are congruent to each other. The dangerous thing about that, guys, is if you come back and look at this again later, it can look like that information was presented at the beginning of this setup, and that's really the conclusion that we're able to draw. Now, guys, we're not doing a whole lot with formal 2-column proofs in here this year. The reason this works, in fact, let me get rid of those for just a second. The reason this works, and this is going to tie back with what we talked about in 4.1, and then this year I'm going to come back and talk about later in 4.2 and 4.3, is if you drop what's called an altitude right here down the center of this triangle and create a new point here that's point D, in a way that we'll be able to demonstrate a little bit later on in this chapter, those 2 little triangles, boy, I didn't draw that very well, but triangle ACD on the left and triangle ABD on the right, those 2 triangles are congruent to each other. The reason why? Well, what I did, and I didn't say this at the time, that point D that I created on the bottom is really the midpoint of line segment CB. So that means that segment CD is congruent to segment BD. And both of those 2 little triangles share line segment AD. So in a silly way of looking at it, AD is congruent to itself. So what's going on right here, this will make some sense for us next week when we talk about this, these 2 triangles are congruent. Triangle ACD is congruent to triangle ABD, And the reason for it, which we haven't talked about just yet this year, guys, is by something called side-side-side congruence. Those two triangles have 3 pairs of congruent sides. And once we know that the triangles are congruent, all of their pairs of corresponding sides and all of their pairs of corresponding angles have to be congruent. Well, you can see here that C is the middle letter in the first triangle, and B is the middle letter in the second triangle. So that tells us now that angle C has to be congruent to angle B because those two triangles are congruent. Okay, so that's what that means. I don't want you to worry too much about what I was attempting to do right here with explaining that. This is one that kind of passes the eye test. You can kind of look at that diagram and go, yeah, I get it. You cut that triangle perfectly in half and there's symmetry now. You could fold this thing over line segment AD and angle B and angle C would match up, and sure enough, they would be congruent. So let's look at an example here. I don't think I drew a very good diagram, guys, but that doesn't really matter. We're going to solve for X in this problem. Well, what have we been given, everybody? Let's not make any assumptions. Let's just base this off of what we know. Pretty clearly, I see a triangle. I see a polygon with 3 sides. And within that triangle, I see tick marks here on the left and here on the right. That means that this is an isosceles triangle, although that's not hugely important. I see 2 congruent sides, and if I go back to the theorem 4.3 that we just talked about, if a triangle has 2 congruent sides, then it must also have 2 congruent angles. And those 2 congruent angles have to be opposite from the congruent sides. So this side over here on the left is opposite from this angle, and this side over here is opposite from this angle. All right? So that's a neat little diagram I just drew there. So those 2 congruent sides on the left and right mean that these 2 angles down here have to be congruent to each other as well. And a fundamental idea of geometry that I'm hoping you guys now have down, if we know that these 2 angles are congruent, that means that their measures are equal. So 11x plus 2, the measure of the lower left-hand angle, has to equal 6x plus 37, which is the measure of that angle there on the right. And solving this really shouldn't be all that bad, everybody. I'll subtract a 6x from both sides. That brings all the x's left. At the same time, I'd like to move all the constants right, so I'll subtract a 2 from each side. 2's on the left cancel, 6x is on the right cancel. 11x minus 6x is 5x. 37 minus 2 is 35. And lastly, we'll divide both sides by 5 here, pretty as you please, and get x is equal to 7. That's all the directions said to do there, everybody. All right, so we're done. Never a bad idea, though, to plug that value back in and make sure you see what you expected to see. If x is 7, then let's find that angle measure right there. 11 times 7, last I checked, was 77, and 77 plus 2 is 79 degrees. Over here on the right, 6 times 7 is 42, and 42 plus 37, sure enough, is going to get us 79 degrees as well. Now guys, I didn't think real carefully about this problem when I made it. Those 2 angles right there certainly could be 79 degrees, but they don't look like 79-degree angles to me. If I asked you guys to go further now and find the measure of this, the vertex angle of that isosceles triangle, well, now that we know the measures of 2 angles, 79 and 79, we can absolutely come up with the measure of the 3rd angle. So what would I do here? I would take the sum of all 3 angles, which is 180, and I would subtract each of the 2 angles that I already know. And I am pretty sure, guys, that that is only going to leave you with 22 degrees for the measure of this angle right up here. Now, the point I wanted to make, everybody, is it certainly looks like that angle up on the top is obtuse. But the math actually showed us that that's an acute angle, and a small one at that, 22 degrees. So my figure is not drawn to scale, everybody. It probably would have been more accurate for me to draw a triangle that looked maybe something like that, with a really skinny angle up on the top. That looks like that might be 22 degrees, and now that these 2 angles on the base here would both be 79. But I guess that proves the point, everybody. Don't spend any time thinking about, does it look realistic or not? You can't assume that an angle is acute or obtuse or big or small just based on the diagram. It's the numbers, the analysis, everybody, that tell you whether that's the case or not. Okay, let's run with this one right here, theorem 4.4. This one is just the converse of the theorem that we just wrote. And a converse, everybody, takes the if and the then in an if-then statement and flips them around. So theorem 4.3 said if two sides are congruent, then the opposite angles are congruent. The converse flips that. If two angles of a triangle are congruent, then the two sides are congruent. So this diagram would look similar to the last one, everybody, but now we're kind of doing this in a different order. So let's see, I did X, Y, A, B, and C last time. Let me call this triangle, we'll go J and K, and we'll put an L right over here. And now, the hypothesis of this theorem says if two angles of a triangle are congruent. Okay, you know what? I've drawn too many of these triangles in exactly the same way. So you know what? I'm going to mix this up just a little bit. I'm going to draw it differently, guys, after all. I'm going to do something like this. Okay, just so we get in the habit of not seeing things in the exact same way. So J and K and L, there we go. And now the hypothesis says that two angles of that triangle have to be congruent. So I'm going to say, everybody, that angle J is congruent to angle K. That's the hypothesis. If angle J is congruent to angle K, all right, then let's go back up and read the formal version of it right here. Then the sides opposite from those angles are congruent. Well, I think you know where we're going with this. The side opposite from angle J is this one right over here, LK. And the side opposite from angle K is this one right over here, JL. So however you want to name those, we could now say that line segment LK would have to be congruent to line segment LJ. Okay, that would be the conclusion of that one. And again, the reasoning is really the same, guys. If I were to find the midpoint of JK, let me call that M, which is a good letter to use for midpoint. I wish I could say I planned it that way, but I didn't. Anyway, if we put M right there, what do we know? M is the midpoint of JK, so that segment is congruent to that segment. Segment LM is congruent to itself. Okay, and with that in mind, everybody, a couple of different ways of going about this, but we would know here, everybody, let's see, that those two triangles would have to be congruent because of some other methods that we haven't talked about just yet in this chapter. We'll get to that a little bit later, but once again, most people will look at that diagram and go, oh yeah, I can see that the triangle on top, triangle JLM, let me go ahead and write that down, triangle JLM would have to be congruent to the triangle on the bottom, which would be KLM. And that now tells us, everybody, that LK, let's see, and LK represent the first two letters of that triangle, would have to be congruent to LJ, which are the first two letters of that triangle. Okay, nothing too bad here, guys. All right, let's go just a little bit further now. Theorem 4.5 is another useful one right here. If a line bisects the vertex angle of an isosceles triangle. All of that is the if, everybody, and again, that tells me what to draw. A line bisecting the vertex angle of an isosceles triangle. Okay, so let's start with the isosceles triangle. And again, just to make it different, you guys, I'm going to draw an isosceles triangle that looks something like this. Okay, and I'm going to connect those two pieces. And what I tried to do there was to make this side congruent to this side. All right, so let's name some things so we know what's going on. I'm going to go to the end of the alphabet now and go, this will be point X, and this will be point Y, and this one here will be point Z. So we have an isosceles triangle, and we're supposed to draw a line that bisects the vertex angle. So you might need to go back now and check your vocabulary. I doubt that you guys know it just yet. The vertex angle of an isosceles triangle is the angle between the legs. The legs of an isosceles triangle are the two congruent pieces. So line segment YZ is one leg, and line segment YX is the other leg. And that means that angle Y right here, everybody, is the vertex angle. And we're trying to draw the line now that bisects that vertex angle. Bisect meaning cutting it equally in half. So I'm going to draw the line that passes through Y, okay, that bisects that angle. Bisect means this angle here is going to be congruent to this angle right over here. All of that, everybody, is the hypothesis of this theorem. If a line bisects the vertex angle of an isosceles triangle, and now it's time to start reading the conclusion now. So if all of that happens, then that line, what we have drawn in red, is also the perpendicular bisector of the base. Okay, this point right here, guys, where that red angle bisector intersected the base of our triangle, I'm going to name that point W, just so we have something going on here. And the phrase that's important right here, guys, is a two-word phrase, perpendicular bisector, okay? It means kind of what it says. First of all, it's perpendicular. So our conclusions here, guys, would be that line segment, line YW, and you could either make a segment out of that or a line, YW has to be perpendicular to the base of that triangle, which would be line XZ. So that's one conclusion. That takes care of the perpendicular part. The other word that's important that we haven't used a ton in here this year, although we have learned it, is bisector. And a bisector, everybody, cuts something into two congruent parts. That means that when we draw that red line segment and we locate point W, this segment over here on the left, XW, and this segment over here on the right, ZW, have to be congruent to each other. Line segment XW is congruent to line segment ZW. Okay? And yet again, everybody, that is because when you draw this line down the middle of an isosceles triangle, you create two congruent triangles here. You don't need to write this down, guys, but as we look at it, triangle, what do I want to call it? XWY is going to be congruent to triangle, and that's going to be ZWY. All right, and that fact right there is what leads us to these conclusions right over here on the right-hand side. Okay, so let's see that theorem illustrated for us real quickly here, guys. We're going to try to solve for y and z in this figure. So, what are we looking at? I don't want to base any of this on visual assumption. I want to take a look at what's going on. And I realize now it was probably a poor choice for me not to give some letters right here. So, I'm just going to pick it up at Q. How about that? So, this is point Q and R. This point here will be S, and we'll put a T right over here. Interesting question. How many triangles are in this figure? A lot of people want to look at this and say 2. They're talking about triangle QST, okay, which is this triangle right here. And then they see triangle QSR, which is this triangle right here. But there's also a third. And that's the big outer triangle, which is QRT. Now, if I focus on that big outer triangle, I can see, guys, the triangle QRT is isosceles because it's got a tick mark here on QR and a tick mark here on QT. So we're dealing with an isosceles triangle. And let's take a look. These tick marks here and here tell me that within this isosceles triangle, line segment QS is bisecting angle Q up on the top because we have two congruent angles. So if I go back and read this theorem again, if a line bisects the vertex angle of an isosceles triangle, what's happening here? We have an isosceles triangle because of these tick marks. Those two sides are the legs. The other side, down here on the bottom, is the base, and the angle up here on top is the vertex angle. So what's happening, guys? We have a line, QS, that's bisecting the vertex angle of an isosceles triangle. So yes, this theorem applies to the diagram that we're dealing with in this example. The conclusion of this theorem now tells me that that line is also the perpendicular bisector of the base. And that tells me two important things. For starters, it tells me that line segment QS has to be perpendicular to line segment TR. And right away, guys, what does that tell us? Y has to be 90 degrees. All right, or y has to be 90, and the angle measure has to be 90 degrees. That takes care of the perpendicular part. The other important part, though, is that it's a perpendicular bisector. That tells us that point S is the midpoint of TR, and that these two segments down here on the bottom have to be congruent. So where do we go next? 5z plus 3 has to be equal to 8z minus 9. All right, we're going to solve this real quickly, guys. I'm going to bring the 5z over here, bring the 9 over to this side. The 3 plus the 9 is going to make a 12. 8z minus 5z is going to make a 3z right there. Nobody likes it when I do the arrows, I get it. Divide by 3 on both sides, we're going to get z is equal to 4. Okay, so we were looking for the value of y, found it, and the value of z right over there. Okay. Last two things to talk about real quick, then I might throw another example or two at you. Let's see where we're at. Corollary to theorem 4.3. A corollary is something we really haven't talked about very much at all this year, but there are three ideas in geometry that go together: postulates, theorems, and corollaries. All of them are true, all of them are laws. A postulate is something we know is true that can't be proven. A theorem is something we know that's true that can be proven, and a corollary is just a little tag-along idea that goes with a theorem. It's not important enough to be its own theorem, but it's just taking an idea one step further. And this corollary says something that I think you guys are going to understand quickly. If a triangle is equilateral, then it is equiangular. Okay, so what are we going to draw? I'm going to draw a triangle. Not going to spend too much time, but you'll notice I am kind of trying to draw it a certain way. And again, let's go ahead and label things. Let's call this one S, and this point here is going to be T, and this point over here is going to be U. So triangle stew, we'll call it that way. And the corollary says, if the triangle is equilateral, that, the hypothesis, is what I draw. What does the word equilateral mean? All three sides have to be equal or congruent. So SU has to be congruent to ST, which also has to be congruent to UT. And the corollary now says that this triangle would have to be equiangular. Well, to prove that, let me actually get rid of my last tick mark, and let me assume for just a moment that this triangle was isosceles. We learned a theorem here. I think it was 4.3 a minute. Nope, 4.4. No, 4.3. Nope, it was 4.4. Sorry. If two angles of a triangle are congruent, hang on a second. Here we go. I'm sorry, it is 4.3. If two sides of a triangle are congruent, then their opposite angles have to be congruent as well. So where are we right here, guys? In this diagram, we've got two congruent sides, SU and ST. Therefore, their opposite angles have to be congruent as well. Which angle is opposite from SU? That would be angle T. And which angle is opposite from line segment ST? Well, that would be angle U. So those two congruent sides make these two angles congruent. But wait, there's more. If the triangle is actually equilateral, now, yeah, I've got to put a tick mark right here as well. And now, if we were to focus on this tick mark and this tick mark, their opposite angles have to be congruent to one another as well. So, what angle is opposite from line segment SU? Well, that would be angle T. What angle is opposite from line segment UT? Well, that would be angle S. That has to be congruent to angle T. And now what we realize here, everybody, is that basically this is kind of the connection here between isosceles and equilateral triangles. If all three sides are congruent, then all three angles would have to be congruent as well. And just going a step further here, equiangular means equal angles. If the sum of your three angles is 180 and they're all the same, you could find the measure of each one here just by dividing by 3. So in every equilateral or equiangular triangle, your three angle measures are always going to be 60, 60, and 60 every single time if your triangle is equilateral. And the last corollary is the converse of the one we just did. If a triangle is equiangular, then it is equilateral. So the diagram's going to look more or less the same. I'll try to draw it a little funky over here, guys, but there's only so much I can do. All right, and let's call this one triangle D, and E and F. All right, what do we start off knowing now? If the triangle is equiangular. Equiangular means all angles are congruent. So if angle D is congruent to angle F, let me just stop right there. If a triangle has two congruent angles, nope, this one here. If two angles of a triangle are congruent, then the sides opposite those angles are congruent. Oh, so where were we right here? Two congruent angles means that their opposite sides, this one over here and this one over here, they have to be congruent to each other as well. So line segment DE has to be congruent to line segment FE. But let's go further. The fact that it's equiangular means that angle E has to be congruent there as well. So if we were to focus on angle F and angle E, these two angles are congruent, and their opposite sides, which would be DE and DF, well, they have to be congruent as well. Since DE has a double tick mark, DF is going to get a double tick mark as well. And what do you notice now, guys? All three sides of that triangle are congruent, which makes the triangle equilateral. Okay, two more quick things I want to do with you guys, and then we're done here. I don't have any numbers for these, but once more, we're just going to find x in this problem over here. I meant to get these ready and I forgot to. So I'm going to draw a triangle that looks equilateral, but I'm not necessarily going to give you the tick marks that you might want to see here. And I'm going to tell you guys that this angle, that line segment and this line segment are congruent. Actually, we're only going to do one more of these, okay? And I'm going to tell you guys that this angle right here is going to have a measure of 3x. Oh, I'm going to regret not doing this ahead of time. I'm going to go with something like 3x plus 5 degrees for that angle right here. And that this one down on the bottom is going to have a measurement of, oh, think, man, think. Yep, I'm definitely going to regret this. All right, this is going to work out ugly, and that's okay. I'm going to say that this angle is going to be x minus 2 degrees, and we're going to solve for x in this problem. Now, this example looks a little bit like what happened here in the example that we did right here. Now, in this diagram, before I marked it all up, we had a triangle that looked like this with two congruent sides. That made it isosceles. And knowing the measure of this angle and the measure of this angle, those were the two base angles. In an isosceles triangle, they had to be congruent to each other. Now let's take a look. Is the same thing happening in this problem right here? No. Again, if I were to label everything, which I should have done early on, I'll go with triangle NO, and we'll put a P right over here. So triangle NOP, this is an isosceles triangle, but ask yourself, which two sides here are congruent? The answer to that is line segment NO and line segment PO. It is the angles opposite from or across from those two sides that have to be congruent, guys. So angle P is congruent to angle N, okay? Angle O here is actually the vertex angle of this triangle here, okay, between the two legs. So what that tells me, everybody, is that angle N up here on the top is congruent to angle P. So the measure of angle N must also be 5x minus 2 degrees. This angle and this angle have to be the same. So now, everybody, we don't know the relationship between this angle and this angle straight up, but we now have a representation for all three angles in this figure. And we know that in any triangle, the sum of your three angles must always be 180. So we can now say 5x minus 2 plus a second 5x minus 2 plus a 3x plus 5 has to equal 180. See, once you know two angles in an isosceles triangle, you can always figure out the third. Now, I didn't plan this well, so I think this is going to work out poorly, but we'll run through it anyway. That's a 13x, and then a minus 2 plus 5. That is a plus 1. That equals 180. Oh boy, 13x then is going to equal a 179, and dividing by 13 is never going to work out clean here. So I'm going to go ahead and grab a calculator here, guys, and type in 179 divided by 13, and I get x equals 13 we'll call that 77. Okay, if this was a test or quiz question, I would have planned that more carefully and probably had it come out to be an integer. Just wanted to show you guys how to do a problem like that. All right, everybody, that's a wrap on section 4.5. Let's give that homework a try and let's see how we do. Good luck.